Hi class, I'm going to cover now an introduction to medical imaging. So this should be kind of a precursor to you reviewing for or reviewing your convolution, your Fourier transforms, Fourier series, all that stuff. So take a look at it, but let me give you some motivation for why you want to even look back into that. So, so we're going to talk in this set of lecture slides about the different anatomical views and planes, and we're just going to briefly cover. It's kind of like an overview of the different technologies we're gonna be discussing in the rest of this class. And I think the most important probably message for the whole entire lecture. Obviously, the details are important, but we're going to see that different medical imaging technologies, they use different types of energy. So it could be radiation, ultrasound, or acoustic waves, same thing, or magnetic spins in your body, and basically use them to map uh, your body and your organs, and to basically make distinctions between different tissues. And then at the very end, we're just going to cover the concept of pixels, which most of you are already familiar with, but we'll dive into that as well. All right, so let's talk about some anatomical views and planes. All right, so when we're talking about imaging, let me kind of back up a little bit and give you some context as to why we're going into this. So, the beginning of this class, we basically talked about different ways to diagnose people with different diseases. We didn't get into the diseases part, but we did cover different technologies to measure things like blood pressure, or really any pressure in the body for that matter. We were able to also measure cells using a Coulter counter, so like distinguish between different kinds of cells and the shapes of cells and the sizes of cells. That has implications in terms of like sorting cells and being able to maybe even count the number of like white blood cells to maybe to diagnose maybe some immunity issues. We also covered ECGs, and we didn't get to EMG and EEG, but we'll cover that when we're in person. But so that these are all measurements that you can take basically on the body that give you some type of diagnosis, or it gives a doctor basically a view into the health of your body. Okay, so now, but these are all just indirect measurements of what's going on with your health. So it's sometimes very instructive to actually see things. So in order to like detect cancer, you may be able to like detect secondary side effects. But actually being able to see a cancer and a tumor would be more helpful, obviously, in diagnosing the cancer than would be to take different measurements and kind of infer that a person has cancer. So so this slide basically is giving you an idea of the types of views you can take when you're basically carrying out imaging. So these are pretty much definitions, and they're gonna come in handy when we actually start seeing different images, whether it be an image from an MRI, an ultrasound, or an X-ray as well. So when we talk about an anterior view, anterior just means the front. So any view of the body that is labeled as an anterior view, that means that the observer is basically looking at the front of the patient. And you're probably wondering, well, duh, I can see this picture here. The guy's facing me, so duh, he's definitely, I see his front. But there's going to be images where you're not seeing a person's face. Maybe you're seeing just their heart, and it's a slice of their heart. And I'll get to slice in the next couple of slides. But you're basically looking at these sliced images of a person's body, and it may not be readily apparent what view you're looking at. Is it the back of the heart, the front of the heart? which way are we supposed to, which is our orientation basically, or what is our orientation. So when a picture is labeled anterior, that means that the observer, you, is looking towards the front of the patient. Um, there are these other kind of secondary definitions here. So proximal and distal. Proximal means in reference to the person's torso. So proximal means that that body part is closest to the torso. Distal means that you're further away from the torso. Now, this is all relative, right? There's no set cutoff where exactly you begin to say that this part is proximal and then this part is distal. It's all relative. So, you would say that your index finger is more distal than your forearm, for instance. That's just another way of saying that your forearm is closer to your torso than your finger is. All right. The other type of view is lateral view. So this is basically a side view of a person. So sometimes you'll see again another slice of a person, maybe their interior organs. But basically, when it's a lateral view, it's a side view. One other definition is superior versus inferior. And this might be a little bit obvious from, if you were paying attention to the naming of some of the blood vessels. But superior means towards the head, inferior means away from the head, toward the lower extremities. So, if you recall, there's two veins called the inferior vena cava and the superior vena cava. The superior vena cava, as it's labeled superior, comes from the head, and the inferior one comes from the lower extremities. Again, just like proximal and distal, there's no exact location where it becomes superior and inferior. It's just in reference to another body part, for instance. And then lastly, you have a posterior view. That is when the observer is looking at an image from the back of the patient. And the secondary kind of definitions here are lateral and medial. Medial is basically at the midline of the patient. So if you were to basically get this imaginary line and go all the way to the patient, and you would cut this person, you would have pretty much a symmetric view of this person on each side. That's the medial line. That's where your reference is. So anything that's closest to the medial line is medial. Anything away from the medial line is lateral. Okay. I'm not gonna ask you to memorize, or I'm not gonna put this picture up in an exam, but again, it's for your reference. So if I throw up a picture of an MRI and it's labeled anterior view, medial, or something like that, then you know exactly where the definitions come from. Okay, so I've been mentioning this word slice here, and you're probably wondering, what do you mean by slice? And so, basically, using the definition from before, we can define basically a lot of, or infinite number of planes that you can view the patient from. So the first one we'll label is the frontal plane, and so this goes back to this definition. So the frontal plane is an imaginary plane that basically cuts the body into anterior and posterior sections. So imagine there's a plane that goes down, the middle of your body on the frontal plane, and then separates you and cuts you open in that sense. So that's the frontal plane. There is another one called the mid-sagittal plane. Remember the midline I mentioned before? I think I called it medial. The midline here. So the midline, the mid-sagittal plane basically is the plane that cuts the body in symmetric halves. So obviously we're not all symmetric, but for the most part you can assume we are at the mid-sagittal plane. Any plane that is parallel to the mid-sagittal is called the sagittal plane. So there can be a plane that's 1 millimeter away from the mid-sagittal to the right or left, and that would be called the sagittal plane. Um, this is important because obviously you have multiple organs in your body and they're located at different locations, and so it would be kind of useful for the doctor to be able to pick what plane and any parallel planes to that reference plane to take images at different locations in your body. And then you have a transverse plane, that's the circle one here, that's perpendicular to the mid-sagittal and the frontal plane. And again, you can have a frontal plane and you can have another parallel plane to the frontal plane and also to the transverse plane. So if you wanted to image something on the heart, you can either use transverse, mid-sagittal, or frontal plane, or anything parallel to each of those planes to take an image of the heart. Okay, so let's get into the actual medical imaging stuff. Okay, so here's a motive for imaging. So like you've already kind of noticed, the human body is pretty complex. There's multiple systems working together. Those systems are like the cardiovascular system, the respiratory system, and all those. So taking images of the body is probably the most efficient way to acquire data and the status of patient's health. And so doctors always use these images to diagnose problems. Okay, there's a couple of things that medical images can really reveal. They don't just take pictures of images, and the method by which they take pictures is important. But really what they reveal, without getting too much into it now in this slide, is an image basically reveals a tissue's opacity. What that means is like its ability to absorb or attenuate a specific kind of energy, its reflectivity, its conductivity, and its magnetizability. So you can imagine that magnetic resonance imaging has something to do with the magnetizability of different tissues. And you're probably curious, wait a minute, my organs or my tissues are not magnetizable. Well, it turns out they are. They're not very good magnets, but you can magnetize them, and you can actually use that to basically take images of different tissues. All right, so let's get into so knowing that images are basically imaging the properties of tissues, the different properties. Let's talk about the different energy sources and tissue properties that are essentially measured and then translated into images for the doctor to see. So I think the most familiar one for everybody is an X-ray. I mean, hopefully you've all gone to the dentist and you had your teeth imaged to make sure you don't have cavities. Well, so that is one form of medical imaging, X-rays, and so that uses a source of X-rays, which is basically radiation. And what you're really measuring in the tissue is the mass density of tissue. So what does that really mean? So if you recall, when you go to the dentist's office, they only want to image your teeth, so they put this really heavy looking jacket thing on you, and basically that has lead in it. So lead has a really, really, really high mass density. And so what happens is when they do apply radiation into your head, basically, they limit the exposure of other tissue to the X-rays by basically covering it with lead. Because lead has such a large mass density, it actually absorbs X-rays. So no X-rays get transmitted through the lead, and because your bone is not as dense as lead, there is some transmission of X-rays through the bone. But it turns out, so you're probably wondering, wait a minute, so then how can I actually see my teeth? Well, in comparison to the tissue around your teeth, the tissue around your teeth have a really low mass density. And so what you get is, if you were measuring the lead, you'd have basically no transmission of X-rays. If you're measuring tissue, you'd have a bright image, or what I should say is black image, because all the X-rays go through. And if you were to measure the lead, it'd be white image because there's nothing that hits the screen. And then you have your bone, which is in between. And so that's how you're able to basically distinguish. And so what you're really measuring on the image, so when you finally get the image out, what you're measuring is the transmissivity of the X-rays through the tissue, and that's a function of how dense the tissue is, which we can test by putting X-rays in the body. So that's kind of how it's going to go. So I'm going to go through the table here to kind of give you some ideas. So the other one that we cover um, is basically annihilation. So this is going to get to when we talk about um, nuclear imaging. That's not like X-ray imaging. It's going to turn out that we're going to be able to inject some chemicals in the body that are radioactive, and when they basically chemically react with other chemicals, you're going to be able to see the conductivity on the image of that tissue. Another one is ultrasound. So that would be basically a source of acoustic waves. What you're really measuring is, the volume of blood, but also really, this is kind of misleading. You can measure this, but what you're really measuring is the acoustic impedance. So the ability for the tissue to uh, basically reflect acoustic waves through the tissue. And so that's what you'll see basically. It's basically absorption, which you're measuring in that case. Um, Magnetic fields is MRI. So in this case, you're applying some magnetic fields in the body, causing what's happening in your tissue is you have current flow. Basically, what you have is a magnetization of some tissue, and then that again is basically resonance that you're measuring of different tissue that you're magnetizing at different frequencies that you'll see later. So this is the take-home message of this slide: is that medical images are pictures of tissue characteristics that influence the way energy is transmitted, reflected, and emitted by the human body. So they are related but not the same as the actual anatomy and physiology. So when you see an image, you're able to see the organ, but what you're really seeing are these tissue properties on that image. And that's important because there's some limitations and advantages to certain technologies, and those limitations and advantages are tied into what exact property you're measuring in those tissues. Okay, so let's give you some history here. So it turns out that imaging really has been driven by the advancement in other fields. So an example of that would be like these rare earth fluorescent compounds. So these were used for space exploration, but it turns out that you can basically attach fluorescent compounds to molecules and inject them in patients safely. And by being able to measure the fluorescent characteristics of that compound external to the patient, you're able to basically create a map of the internal organs or the processes in the patient. Scintillation detectors and radioactive isotopes, which are used in CT scanners, those were basically developed for the Manhattan Project, so the atomic bomb. And ultrasound wasn't originally made for detecting the fetus in a pregnant woman. They were actually for military applications, and specifically they were used for sonar and submarine detection during I think World War II or World One. I have to double check that. I think it was World War One. So a lot of these imaging developments came from basically military like research. Um, some other advancements that maybe weren't specifically tied to military is the math that goes behind converting the data from CT scanners into actual images, and also the techniques that have evolved what's called nuclear magnetic resonance, which was basically used to image chemicals, into magnetic resonance imaging, which is obviously used to measure or to image the human body, which is kind of a crazy jump if you think about it. I mean, you have a technology that was used for just looking at the characteristics of different chemicals and the orientation. So this is really used like in organic chemistry, this technique, and you're able to basically, as the foundation, then convert it to MRI to image an entire body. Okay, some more history. In 1895, this physicist by the name of Röntgen, he basically experimented with X-rays that could penetrate materials. So this was the first time that X-rays had been basically used. The most the where it really started being used was actually, sorry. So this is he actually imaged his bone in this case. Sorry, I got confused. I think this was I kept thinking this was a Curie picture, but it's not. In 1946, Felix Bloch and Edward Purcell. The Bloch and Purcell will come. That will be driven home when we actually talk about MRI machines. You're going to talk about the Bloch equations and the Purcell pulse sequence. They were actually the ones that discovered the magnetic resonance phenomenon. And by 77, the first MRI scanner was basically built by Raymond Damagian. So again, this was from the experiments done with nuclear magnetic resonance. Okay, so let's talk about the different types of imaging technologies. And so for the next couple of slides, I am basically going to cover in very brief detail what these technologies are. Alright, so the first one, again, like I mentioned before, that's most obvious to most of you, is what's called radiography. That's another word of saying X-rays. So the way this works is you have an X-ray source, and you have X-ray detectors, which can be either films or electronic detectors. Nowadays we use electronic detectors. And they use very fast exposure to X-rays. Obviously, X-rays can cause cancer. They do that by basically causing a radicalization of some of the chemicals in your body, which can then lead to cancer. So the X-rays pass through the patient, and some get attenuated. So attenuation is basically a word that means that when an X-ray passes, it's passing in a line, and the tissue can then redirect that X-ray in a different direction, or reduce its. Oh yeah, basically it just spreads it out. The more dense a material is, the more likely it is to either absorb it or attenuate it in a different direction. So this is the type of imaging that's called a transmission imaging and a projection imaging. So we'll get to projection later. We're actually gonna talk about how we can basically make an image from just a series of projections. And so the way this works is that each point on the image, on like down here in this image of the lungs, each point on the image corresponds to the information along a straight line through the patient. So that's actually really, really important, because that's gonna allow us to get contrast. So if in this case, and the other thing I forgot to mention is that you can modulate the energy of the X-ray source, which then leads to different transmission characteristics. So for instance, like a high energy X-ray source, would penetrate even some relatively dense materials. So like in this case, these are the lungs. And so what you're seeing is the black areas are the areas where X-rays were transmitted almost completely. So here's air, 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 and these are the lungs. Lungs are basically filled with air. And so the X-rays then pass all the way through, and you basically see the image as black. Anything that was attenuated or absorbed is seen as basically white. So here you can see kind of some bone structures that absorbed the X-rays. So that's one type of imaging. Okay, there's also fluoroscopy. This is under the umbrella of what's called nuclear medical imaging. This is similar. You are using radiation or radioactive source. It could be X-rays, it could be gamma rays. But the difference here is that you're using a chemical that you can inject into the patient to basically enhance an X-ray. So what you're doing is you're taking an X-ray machine, you're injecting the patient with some, like say some dye that maybe has a relatively higher a mass density than the other tissue, and so you're able to kind of like highlight different parts of the body. So, like in this case, for instance, there's a contrast agent or a dye that's basically injected into the patient that then they can image the intestines of the patient. Mammography is a specialized version of X-rays. It's for the detection of breast cancer. Uses lower energy X-rays, and the reason for that is because breasts are usually made of just fatty tissue, and so to be able to image or to distinguish between tumor tissue and fat tissue, you have to have lower energy, because if you have too high of energy, then you're basically going to get no contrast. And the equipment's also specifically designed for measuring in the breast. Computed tomography is also a form of X-ray imaging, but in this case you don't have a static plane that you're imaging on. Here what you have is basically a rotating X-ray tube that goes around the patient, and then you have some sensors that are also rotating, and what you basically get are you get various projections. So you can image on one plane and then change the angle of the X-ray machine, image that plane, and you're going to get a set of projections of the person's body, and then you're going to have to convert that to actual images of the patient, which is not as easy as it sounds. This gives you the ability to display different slices of images. So like in the previous cases, you're limited to basically like one plane, and you can't basically go any deeper. So this is just imaging the transmission properties, but obviously the transmission properties can change along the depth of the breast in this case. So that would be difficult to detect unless you were maneuvering the breast in different directions, which they do. In this case, you don't have to move the patient. You basically just move the source and the sensors, and you're able to then automatically get some images out. Okay, these are another case of nuclear imaging. So here, so there's single photon emission computed tomography, so it's called SPECT. Here, basically, you are injecting the patient with chemicals that emit gamma rays, and this is really useful for measuring physiological processes, not just the anatomical parts of the body. So the way this works is you're basically injecting the patient with gamma rays, and typically, with chemicals that emit gamma rays, and typically those chemicals or those what are called isotopes, radioactive isotopes, they actually are chemically bound to a chemical of interest. So for instance, like glucose. And you're able to basically see like the different parts of the body depending on where you're injecting the chemical, what kind of processes are happening. So like an example of this would be measuring like the brain and the different processes. So this is a picture here of you have these different colors that basically have to do with the intake of glucose by some parts of the brain during different processes. I guess when you're supine, upright, and there's someone that has smoked, someone that has been using nicotine gum, for instance. So what SPECT does is that when once you inject the chemical, that chemical then goes to a specific location, and a process happens, and you're able to basically image the consumption of glucose, or the reaction of a certain process, because you have also that radioactive isotope that's emitting radiation, so you can see the location of where that's coming from. You also have positron emission tomography. It's basically, again, you use radioactive isotopes, and again, they're also easily metabolized. What that means is easily eaten up by the body. So you have some detectors that are able to basically measure those gamma rays. And so what I'm showing here basically is that this would be a typical like CT scan. So you can see an anatomical view of the body, and then this would be the PET image of that. And what you can do is, what you've basically done is you've taken the anatomical data, on top of it you've superimposed some physiological data, and that basically is giving you both anatomical and physiological information. So like in this case, you can see that the brain like the red, really has to do with the amount of uh, the amount of isotopes that you're measuring in that location. So there's a large concentration of isotopes in the brain and other parts of the body, because that's where blood flow is the highest, which means that there's more metabolism going on there. Magnetic resonance imaging. So this one here, you have basically you're using magnetic fields that are about 4 orders of magnitude stronger than the Earth's magnetic field, which is really strong. But what that helps you to do is it helps you to basically magnetize the body, and you're able to extract basically topographic information from the magnetic properties of the tissue at specific points. This is one of the better imaging modalities in the sense that you get really good contrast between tissues that generally would have similar attenuation coefficients, similar acoustic properties. So this is a really good imaging modality. There is some limitations which we'll find out later, but the fact that you are able to use the magnetic properties of tissue, and that really originates from the fact that different tissues have different amounts of water content, and the water content has basically a specific magnetization property that you can then image. So what you're basically imaging is the different amounts of water content for the most part. Ultrasound. This one we're also mostly familiar with. This one you have an ultrasound transducer, so it's a transducer that is in contact with the tissue that generates pressure waves, and those pressure waves are on the order of a couple of megahertz. I think 2.5 megahertz is the most common. Depends on the mode as well, though. But basically, the way this works is you have the transducer producing waves in the body, and depending on the acoustic impedance, so the ability of the tissue to reflect some of those pressure waves, you will get some reflections, and those reflections are then read as echoes. But some will go through, some will be transmitted through, and what happens is that the transducer is swept over many angles, and you're basically able to get many reflected waves. And by taking all that information at different angles, you're able to basically map out an image of different tissues. So, like in the case of a pregnant woman, up here is the ultrasound image. The ultrasound transducer, and you have acoustic waves that are being transmitted through. You're gonna have so basically the tissue at the boundary and anything in between will have specific tissue properties. So these really dark lines here are areas of really high reflection. So there's some organ here, some organ here, and then you're gonna have, like in the case of pregnant women, you're gonna have the amniotic sac, which has a lot of fluid in it, different reflective properties, don't reflect as much, and then you're gonna have the baby, and you can see like the bone will give off really high reflection um, waves. The teeth will, or I guess the gums I should say, the bones there, and so that's where you can basically image the outline of the baby because you have different acoustic properties that are being reflected back. Okay, so let's talk about contrast. So what is contrast? It's an important concept because it's basically gonna allow you to see how you can differentiate between, let's say, a kidney's tissues and a liver's tissue. So contrast in an image is the difference in the grayscale of the image. Um, so every imaging modality basically creates some kind of contrast, which are dependent on the properties that you're measuring. So in the case of X-ray, whether it be radiography, fluoroscopy, or CT scanners, what's giving you the contrast is the difference in X-ray absorption, and specifically, it's the X-ray absorption coefficient that you're basically detecting between tissues, and that's dependent on the mass density and the atomic number of the material. In the case of SPECT and PET, it's basically you're measuring what gives you contrast is the ability of some tissue's ability to concentrate a radioactive material, specifically of a specific chemical, in the previous case of glucose. An MRI, what's giving you contrast is a tissue's proton density. So how many protons are in the tissue, but also what's giving you contrast is also the relaxation phenomenon associated with those protons, and we'll get to that later. That's where it gets a little more complicated, but that's also where you can start getting like different slices of a person's body. And ultrasound, as I mentioned before, what's giving you contrast is the acoustic properties of tissue. Okay, so some more definitions about spatial resolution. So it's spatial resolution is the ability to see fine detail in space. So really what that means is high spatial resolution means that smaller objects can be seen or resolved. And so I have a table here that shows you that basically compares the different spatial resolutions of the different technologies that we've talked about. So in the case of like radiography, depending on if it's screen film or digital, you're on the order of 0.08 to 0.17 millimeters. So that's pretty small. But once you start getting into things like ultrasound, you can do 0.3. You can do, for digital mammography, you can get 0.05. Magnetic resonance isn't very good. It's 1, but it does give you good contrast. So you're starting to see kind of the different limitations already. So obviously radiography, even just good old just screen film, gives you 0.08, which is a lot better than magnetic resonance. But the problem here is that this is dependent on a tissue's ability to transmit or absorb X-rays. Tissues like kidney versus liver, they have pretty much the same attenuation coefficients. So you're not going to be able to, even if you were to play with the energy of the X-rays, you're not going to be able to detect the difference between those two tissues. Whereas with the MRI, you're able to detect that difference pretty easily. So there's a trade-off between the spatial resolution you're getting, but also the contrast that you can also get from the different imaging modalities. Look at the nuclear medicine. 7 millimeters. I mean, you would think that's pretty bad, but remember that this isn't really useful for giving you anatomical information. It's more useful for giving you physiological information. So, even if you're limited to 7 millimeters resolution, you're at least able to locate generally where a process that you're interested in is taking place. Okay, and then this is the last couple of slides, or maybe last two slides or three, basically talking about pixels. And so I just cover this because at some point we're going to start seeing actual images and processing them, processing using convolution, Fourier transforms, or on basically what are pixels. So when I throw up a picture here, we can talk about the imaging modality that produced it, but I guess on an engineering scale or an engineering view, from an engineering view, these are just basically pixels. So they're basically an array of numbers that represent the grayscale number at that point. The portion of the image that is represented by a single number is called a pixel. So it's really hard to see here, maybe not so much because these are bad images, but there's a little portion there that represents one number on the grayscale at that location. That is called a pixel, that stands for picture element. For nuclear magnetic resonance imaging, the pixel represents the number of counts of an isotope detected by a camera detector. So that gives you some relation between like what an actual pixel means and what what it actually physically means when you're using different modalities. Here are different images with different number of pixels. So this is a 1024 by 1024. So you have 1024 on the row and the column, and so that gives you a better image than a 16 by 16 pixelated image. Okay, so here are some typical pixel formats for different imaging modalities. So typically, what's produced from X-rays, basically, that's up here, are 64 by 64 pixels or 128 by 128. From SPECT, it's about the same. From an MRI is where you get better. So that's 64 by 64, or it's 1024 by 1024. Mammography gives you the best. We have can go up to 4,800 to 6 by 6,000. This is important for mammography because you have to be able to detect cancer or tumor tissue within the breast, which is pretty hard to detect if you don't have good spatial resolution. So that's why you have that. The number of pixels is much higher in these images than others. Okay. One thing I forgot to mention is the amount of data that's produced by each pixel. So for MRI, you have 12 bits of data per pixel. For mammography, it's also on the order of 12 to 16, so more information per pixel. So this is all going to talking about how much information is encoded in each pixel. So here you have a comparison of different images of different number of bits per pixel. So this has 8 bits of information per pixel. This has 3 bits of information per pixel, etc. Obviously, the more bits of information you have per pixel, the better, because you're able to basically get better contrast within your image. Now, the trade-off with this is that the more bits per pixel you have, the more data you have to store. And considering that this is just one slice of a person's body, like in the case of a CT scanner, this would just be one projection, and you can have many, many, many projections, and so that just then starts to compound with the number of information per pixels that you have. So for those of you that are not really sure what bits means, they mean binary digits, so it allows for the digital representation of data, which gives you contrast. More bits means more information. So like an example, I don't know if I have this in the next slide, I don't think so. So an example would be like, how do you distinguish the different shades of gray? That's going to get broken down into different number of bits. And the less bits you have, the less distinction you have between various grayscale colors of your image. Okay, so each pixel can contain 8 bits of information. Um, if you don't have enough bits, you can have misleading shading. So, like as you're seeing here, 2 bits per pixel versus 8. There's different shading here, so you're able to detect different attenuation coefficients. Whereas here, you're seeing this whole block here as the same attenuation coefficient as everything in here. So, which is not quite true, right? Here you have some contrast here, and here you have no contrast. So it's really important to take that into consideration. And here's just the math to figure out. So determine the number of bytes required to store an X-ray image that is 512 by 512, where each bit is 8 bits. I'm sorry, where each pixel is 8 bits. So here you would just basically multiply the size of the image, so that this is how many pixels you have. Um, uh, there's 1 byte per pixel, so that just tells you how many bytes there are. And so if you just Google this, how many bytes in a kilobyte, then you know that for this specific image, that there's 256 kilobytes of information. So here, if I give you a question like this, you'll be given this table to convert. So obviously, I would say, okay, do this again for like 1024 by 1024, and you're going to see that it's, again, bigger amount of data you have to save. Okay, so next week we're going to start a review of Fourier transforms and convolution, and then after that we'll get to ultrasound imaging. All right, thank you for watching.